Hello. Most programs will make decisions and selectively perform calculations based on those decisions. Decisions made by computer programs are the result of yes/no questions or true/false statements. A common way to make your program selectively execute commands is to use what is called an if block or an if structure. An if structure works almost exactly as you would expect. It checks some condition, and if that condition is true, one associated action is performed. However, if the condition is not true, some other action takes place. There are several variations on this theme. Multiple conditions can be tested, or the structure may do nothing at all. In this video, we'll show you how to use if blocks to allow your programs to make decisions. Here's one example of a calculation that depends upon a condition. The function's defined differently over two different ranges of x. If x is less than or equal to 0, the value of the function is 0. And if x is greater than 0, the value of the function is e to the negative x, or a decaying exponential. Evaluating this function for some value of x requires you to make a decision. Is x less than or equal to 0 or not? This is a graphical description of the decision-making process. First, you need a value for the independent variable x. Next, the decision as to which equation to use has to be put in the form of a yes, no, or true/false question. In this case, the question is x less than or equal to 0? If the answer to this question is yes, we set f of x equal to 0. If the answer is no, we set f of x equal to e to the minus x. Next, let's look at a programming structure, an if block, that can be used to implement this kind of decision-making process. This is the most general form of an if structure. The structure always starts with the word if and always ends with the word end. The if statement is followed by an expression that evaluates to either true or false. Below the if statement is a set of commands that are executed if the expression in the if statement is true. So, if this expression is true, these statements get executed and the if block execution is terminated. The program jumps out of the structure and continues executing any code below the end statement. To check for an alternate condition, you can use an else if statement, which includes a different expression, which is either true or false. If this expression is true, a set of commands below this statement are executed and the if block terminates. You can have any number of else if statements. They all work the same way. If the logical expression associated with the else if statement is true, the associated commands are performed and the program stops checking any other conditions. If the logical expression is false, the program continues to check the remaining conditions in the if block. Make sure that you write else if all as one word. If you type else and if as two separate words, MATLAB thinks that you're starting another if block inside the first if block, and it'll want two end statements. An if block that contains only if and else if conditions might take no action at all. Calculations associated with these statements are only done if some condition evaluates as true. So if none of the conditions in the block are true, nothing gets done. You can, however, include an else statement in your structure if you want to make sure that your if block does something before it terminates. The else statement doesn't have a condition. The commands following this statement get executed as long as none of the conditions preceding it are true. There are a few things that I want to emphasize before doing some examples of if structures. You're not required to include else if or else statements if you don't need them. So you can have an if structure that just says, if this thing's true, then do this, but if it's not true, continue on with the remainder of the program. The program exits the if block once it's gotten a true response to some condition. So if the very first condition you list turns out to be true, none of the remaining conditions are even checked. So only one set of commands in an if structure are ever executed. Commands associated with an else statement are performed if none of the logical expressions in your if block are true. An else statement ensures that something gets done before the block terminates. Finally, if blocks don't necessarily have to result in a set of commands being executed. If there isn't an else statement, it's entirely possible that the if block will have no effect on the code. This isn't necessarily bad. Sometimes you don't actually want to do anything. Now I'll do a few examples of if blocks. First, I'll go back to the example this video started with. The function I want to evaluate is 0 if x is less than or equal to 0, and it's e to the minus x if x is greater than 0. This if structure will implement this function. The structure starts with the word if and ends with an in statement. The if statement first checks to see whether x is less than or equal to 0. If this is true, f gets set equal to 0 and the program jumps out of the block. If this is not true, then f is set equal to e to the minus x, and then the program terminates. This implementation never considers that x will be anything other than a real number, so it doesn't check any other conditions. If x is real, it has to be either greater than or equal to 0 or not. There are a variety of alternate ways this same logic could be implemented. For example, I could invert the logic by first checking to see whether x is greater than 0, then setting f equal to e to the minus x if that's true, and set f equal to 0 if it's not true. Another possible implementation is to always set f equal to 0 and then only change the value of the function if x is greater than 0. This function has 4 conditions. The value of the function is -2 if x is less than -2. It's x if x is greater than or equal to -2 and less than 2. It's 3 if x is greater than or equal to 2 but less than 4. And finally, it's 0 if x is greater than or equal to 4. I can implement this function with an if construction as shown here. In this construction, I'm using the conditions exactly as they're presented in the mathematical representation of the formula. So if x is less than -2, I set f equal to -2 and I don't check anything else. If x is greater than or equal to -2 and less than 2, I do this and skip out of the block. If x is greater than or equal to 2 and less than 4, I set f equal to 3 and stop. Finally, if x is greater than or equal to 4, I set f equal to 0. However, I can simplify the implementation here by taking advantage of the way if structures work. If I keep in mind that we exit the structure after the first time some condition is met, I can do this. My first condition is the same as before. I check to see if x is less than -2. However, I can simplify the second criteria just to check whether x is less than 2. I don't need to check whether x is greater than -2 since the code can't reach this statement unless x is greater than or equal to -2. If it doesn't meet that criteria, this code would have been executed and the rest of the block would have been skipped. Likewise, I don't need to check whether x is greater than or equal to 2 in the next condition. I can't get to that point unless it's already true. And in this version of the code, I'll just use an else statement to invoke the final condition. As long as x is a real number, this is the only possible remaining option. Finally, I'll do an example that's more obviously related to engineering. In this problem, I have a cantilever beam with a point load W applied at some distance A from the fixed end of the beam. We want to find the vertical displacement of the beam resulting from this load at some distance x from the fixed end of the beam. These are the 2 different equations to calculate the displacement depending on whether we're to the left or the right side of the load. These equations are obviously only good for x between 0 and L, which is the length of the beam. I can implement these equations with this code. In my decision-making process, first I'll check to make sure that x isn't less than 0 or greater than L. The deflection doesn't make sense if this is true because the value of x isn't even on the beam. So I'll assign x to be not a number, or NaN. If x is between 0 and L, I need to check to see whether x is between 0 and A. However, if the program gets to this point, I know that x is greater than 0. So all I really need to do is check to see whether x is less than A. Then I implement the appropriate equation. If I get to that point, the only other option is that x must be between A and L, so I implemented this equation using an else statement. There really aren't any other options. Next, I'll use MATLAB to demonstrate implementation of this cantilever beam example. I'll also use this demo to illustrate the modularity that I spoke so highly of when I introduced functions. To show this, I'll break the calculation down into a number of components that illustrate how modular programs are developed. First, I'm going to go to my MATLAB demos folder and create a new folder to hold my files. So I'll cd c:\tim\MATLAB demos. Next, I'll make a folder named Chapter 9 inside that folder. So mkdir Chapter 9. And use the cd command to make that my current working folder. cd Chapter 9. Now I'll create a script file to set up the basics of the problem. I'll name the file BEAMDEFL. First, I need to set my constants in the script file. In the script file, I'll also check to see if the value of x is valid. If it isn't valid, I'll assign the deflection to be not a number. If the location is appropriate, I'll call the function to calculate the deflection. The function is going to accept the physical parameters and return the displacement. I'll also add comments to explain what the code's for and define the constants. Now I'll create the function to calculate the displacement. I'll name it pointLoad. First, I need a function declaration statement. I'll name my function pointLoad. The function accepts the physical parameters as inputs and returns the displacement. I need to keep the order of the parameters consistent between the function calling statement in the script file and the function itself, but I don't need to use the same names. The function checks to see if the position is greater than or less than A and acts accordingly. Notice that I don't have to check whether x is greater than 0 or less than L, since the program can't get to this point if that condition isn't true. Now I can run the program by typing the script file name at the command prompt. The program runs and the displacement is shown. I'll change the location to a distance larger than the beam length to check my logic for catching errors. Now I'll rerun the file. The value of x gets set to NaN, which is just what I asked it to do. But it would probably be good to add an error message to make sure the user realizes what happens. Now if I rerun the file, x gets set to NaN and you get a message as to why that happened. We've developed almost all the tools we'll need in order to do some pretty sophisticated numerical analysis problems. But there are a couple more useful structures that I need to introduce. These are called for and while loops, and they allow you to perform very repetitive processes. They're the topic of the next video.